let's dive right into this explainer. Because right now, a massive, fundamental shift is happening in global materials science. For centuries, we've relied on the incredibly destructive process of extracting virgin raw materials from the earth. But now, we're starting to literally mine our own trash. Today, we're going to explore how some truly brilliant engineering is blending everyday organic waste flows with high-tech molecular grids to completely revolutionize how we build our world.
Here is our roadmap for today. We're going to cover the new materials economy, how we're building with macro waste, the reticular chemistry revolution, in situ growth and biomimicry, and finally, engineering a circular future.
Starting off with Section 1, the new materials economy.
I want you to do me a favor and completely rethink your physical environment for a second. What happens if we stop treating toxic industrial liabilities, agricultural runoff, and ocean plastics as these, incredibly expensive problems that we just have to bury or burn? What if instead we start treating them as high-value critical raw materials? Honestly, it completely flips the global economic equation on its head.
So, what do we actually mean when we talk about a circular economy? Well, a true circular economy isn't just about downcycling our water bottles into lower-grade plastic items. It's about actively re-engineering waste streams into advanced, high-performance structural materials. We are talking about taking everything from everyday municipal solid waste all the way to heavy metallurgical byproducts and using them to build the actual foundations and infrastructure of our future cities. But there is a major logistical reality check behind this shift. Dr. Elsa Olivetti from MIT points out a pretty massive bottleneck, which is supply chain stability. Because think about it, if you're building a multi-million-dollar commercial business on waste, you absolutely need a reliable, predictable supply of it. Her team is actually using artificial intelligence to automatically scan scientific literature and catalog global waste deposits. They're mapping out exactly where specific industrial byproducts are created to ensure that these novel waste-derived supply chains remain steady for manufacturers.
Moving right along to Section 2, building with macro waste.
Think about the total night and day contrast between our past and our future here. Our traditional concrete and kiln-fired brick industries are brutal. They require temperatures well over 1,000 degrees Celsius, they completely deplete topsoil, and they emit literal gigatons of CO2. But the new paradigm? It uses ambient temperature chemistry to bind industrial ash and slag. This preserves our land and actively acts as a carbon sink. It is literally a total reversal of the environmental impact. And the sheer diversity of these upcycling waste streams is just mind-blowing. MIT's Haas Group is doing this incredibly cool thing they call print dirty. They're taking highly contaminated, unwashed, single-use plastics and feeding them directly into decentralized 3D printers. This completely bypasses the incredibly expensive washing and sorting phase of traditional recycling. They can extrude an 8-foot structural floor truss in under 13 minutes. Meanwhile, other research groups are replacing the sand and concrete with copper slag, and they're utilizing crop residues and even chizoton, which comes from seafood processing waste, as primary building blocks.
Oh, and we can actually let biology do a lot of the heavy lifting for us, too. Take structural mycelium, for example. There are initiatives right now like Inua Mycotile in Kenya that are tackling the massive global problem of crop waste burning. Instead of setting fire to leftover rice and wheat straw, they inoculate it with fungal spores. The fungi then literally digest the waste, weaving this dense natural polymer network. Once you dehydrate it to stop the growth, you are left with high-strength, fire-retardant, and acoustic housing panels. It's brilliant.
Which brings us to Section 3, the Reticular Chemistry Revolution. Okay, prepare to have your mind totally bent for a second. 1 gram, just 1 single gram of these newly engineered crystalline frameworks contains an internal surface area equivalent to an entire American football field. I mean, the amount of microscopic real estate packed into a tiny speck of this material is almost unfathomable. And this is the magic of reticular chemistry. It's essentially the science of snapping together molecular building blocks, kind of like atomic tinker toys, into highly ordered, highly porous grids. We call these metal organic frameworks, or MOFs, and covalent organic frameworks, or COFs. Because scientists can control the exact size and chemical nature of the pores in these frameworks, we can design them to act as highly selective molecular traps. We're talking about frameworks that can filter forever chemicals out of our water, capture CO2 directly from the atmosphere, or, and this is wild, pull clean drinking water right out of bone-dry desert air.
And look, this isn't some distant sci-fi fantasy.
From the foundational design principles established back in 2003, we've seen incredibly rapid evolution. By 2018, MOF-based water harvesters were actively being deployed. In 2019, a specific framework called MOF 303 was engineered to rapidly absorb and desorb water, using very minimal energy, pulling moisture from the extreme aridity of the Mojave Desert. This staggering progress actually culminated in the 2025 Nobel Prize in Chemistry. It is a deployed, commercialized technology right now.
Let's dive into Section 4, In situ growth and biomimicry.
But as with any major technological leap, there's a massive bottleneck. When you synthesize these MOFs in a lab, they naturally form as a fine, loose powder. The problem is, if you pack a fine powder into an industrial water harvester or a massive carbon filter, it basically turns into a solid brick. It completely clogs the machinery, air can't flow through it, and the whole system fails. Brilliant atomic chemistry is absolutely useless if we can't physically shape it for the real world.
So, the ultimate fix for this? It's a process called in situ growth. Instead of making a loose powder, engineers take a custom functional substrate, often a structural scaffolding made from upcycled agricultural cellulose or other waste fibers. They immerse that waste-derived scaffold directly into a chemical bath, and the MOF crystals nucleate and grow right onto the surface. Think of it like growing rock candy on a suspended string. You end up with this highly porous, breathable structure that is perfectly coated in active molecules.
This creates an absolutely beautiful techno-organic synergy. We're sourcing cellulose scaffolding from regional farm waste, we're coating it in antimicrobial chitin sand derived from discarded seafood shells to manage moisture naturally, and we're designing the macro shape to be biomimetic, literally mimicking the fractal patterns of plant veins or the natural flutter of leaves to maximize airflow and the capillary transport of water. It is a perfect, seamless marriage of high-tech reticular chemistry and upcycled biologically inspired waste.
Finally, let's bring it all home in Section 5, Engineering a Circular Future.
When you actually combine this kind of upcycling with precise molecular control, the real-world efficiency gains are just staggering. Agrocrete is taking crop residues and industrial slag, preventing toxic open-field burning, and creating carbon-negative housing blocks that are up to 50% cheaper to build with. Our MOF 303 water harvesters, grown right on those waste scaffolds, are pulling 1.3 liters of clean drinking water per kilogram of material every single day, completely off-grid. And innovators like Sublime Systems are taking waste silicates and using electrochemistry, not fossil fuel kilns, to drop the carbon footprint of cement by a massive 90%.
So as we wrap up this explainer, I want to leave you with a bit of a provocation. From printed plastic floor trusses to atmospheric water harvested on fish-scale scaffolds, the science is abundantly clear. When every single byproduct becomes a building block, is anything truly waste? The future of our survival and our sustainability isn't about finding new things to extract from the earth, it's hiding right inside the trash we already have. Thank you so much for joining me on this incredible journey through the new materials economy.